Alright, so now that there's some basis for understanding how the equilibrium constant works, let's go ahead and apply it. One of the first things that we need to talk about is basically looking at the value of equilibrium constants and then making some conclusions about it. So this is a discussion about the extent of a reaction. So the extent of something means, again, how far along has it progressed, where is it kind of going towards, how much of it has been completed. So when at equilibrium, which of the following equilibria consists of more products? So this is going to be something that conceptualizes a very vague idea. So in this case, let's kind of remind ourselves, generally speaking, right, we always have this value K that's calculated by the amount of products divided by the amount of reactants. So when you look at this first equilibria, you see that, it's got some products from reactants. You don't really know or care necessarily what they are. Just know that whenever it's at equilibrium, the value of Kc is going to be 4.56 times 10 to the 9th. All right. That means when you look at this ratio as a fraction, the products divided by reactants gives you a value of 10, something on the scale of 10 to the 9th power. That's a very large number, right? So if you wrote this out, that's 4, 5, 6, 1, 2, 3, 4, 5, 6, 7 zeros afterwards. That's a very large number. So that means the value of P is going to be significantly greater than the value of R. So what does that tell you about the relative amounts of products compared to the relative amounts of R? Is that there's going to be way more products than there is reactants. So in terms of the extent of this reaction, right, which one of these following equilibria consists of more products? Most definitely the first one, by a lot. Because if you look at the second one in comparison, right, still going this idea of products over reactants, that's going to be a value of, 0.211. Now, the value in terms of what is compared to this previous one here isn't that drastic. 0.211, again, is not super large. But what do you notice about the value of the difference between P and R is that R would actually be a larger value, meaning there's going to be more reactants right now than there are in products, because that ratio, when you divide products by reactants, is less than 1, right? 0.211. Now, one thing I just mentioned there that you probably may have caught, but we kind of at least need to talk about some more, is this idea that when K equals 1, that means that the products over the reactants, that should be a P, that means when your products over your reactants, right, that's going to be the same amount. There's going to be the same general ratio, so that's about equal. But when it comes to this idea where it's not equal to 1, you can make conclusions about it. For example, in this one, that if it's less than 1, it's going to end up having a left side, reactant side, in greater quantities than in the product side. So some of the language that we'll see is that when K is large, and we'll just generically say large for anything greater than 1, when K is large, the equilibrium lies to the right, meaning that it's already at equilibrium, right? And then the value will generally give you, or the values of products and reactants, will generally have much greater products. And so since the product side is the right side of the equilibrium, we just say that the equilibrium lies to the right. There are much greater quantities of products when you've established equilibrium. Essentially, a lot of times, especially when you have very, very large ones, like the previous example where it was like talking about 10 to the 9th power, and somewhere in the range, you can expect that to be pretty much going to completion. Whereas, on the other hand, if you have a small value of K, which is, again, essentially saying it's less than 1, we said that the equilibrium lies to the left. So the reaction, as it's written, whatever you have there, doesn't really occur to any significant extent. And that means it doesn't really proceed to the right that much. You have very, very few reactants, very, very few products versus reactants. Remember the value of K, though. This is always something that comes from when you established equilibrium. So if you start off by being given initial amounts, you can't make any kind of comparison. Speaking of initial amounts, that's how we can apply this idea called the reaction quotient using initial amounts. So if you're given a reaction mixture, meaning you're given some mixture of initial quantities of your reactants, or there really is anything, how do you know if the reaction will proceed in the forward direction, meaning it starts making more products? Or how do you know if the reaction will proceed in the reverse direction, where it starts making more and more of the reactant side, the left side? I don't know that just by given a mixture a lot of times. Also, if the mixture is already, how do you know if it's not at equilibrium already, right? So just by chance that the amounts I give you to start, or the amounts given to you at the start, is already at equilibrium. How do you know these things? And that's where we introduce something called the reaction quotient. This is a value that you're going to calculate, and it's going to be compared to K. But first, let's talk about how we calculate Q. Let's say we're given this equilibrium of N2 plus 3H2 in equilibrium with 2NH3. What do you notice is going to be how you calculate the Q? Well, Q, this reaction quotient Q, is calculated by taking NH3 squared, N2, H2 cubed. So basically, you're calculating the exact same way you would K, but if you notice, each of these little equilibrium concentrations, not equilibrium concentrations, but just concentrations, has a little O in front, meaning that's going to be at initial, right? Time equals initial before any reaction has been allowed to proceed. This is not the same as equilibrium amounts, right? Because we don't know if it is. So this is going to be a test. We're going to take Q, and then we're going to see whether or not it's equal to K. And very similarly, we're going to see if it's going to shift to the right, shift to the left, reverse, or go forward. So this is how it works. Right? How we do this is we compare Q and K. 3 possible comparisons. 1, if Q is equal to K, that means that the initial amount you're given is actually already at equilibrium, so there's no reaction that occurs, at least no additional changes that occur. You're at equilibrium, no big deal. What if Q is greater than K? So that test value you give. What if that Q is greater than K? So let's think about this for a second. Remember that K is equal to your products over reactants. Your Q is also technically your products at initial divided by your reactants at initial amounts. So if Q is greater than K, that means your value on top, this is much, much too large compared to reactants, right? This mixture has too many air coordinated products. So what's this going to do? Well, if it's overloaded on the right side, right, again, it's going to do a generic reactants and products. If it's going to be a little bit too heavy on the right side, it's going to reestablish equilibrium by shifting towards the left, right, towards your reactants. That way, the products goes down, reactants goes up, and then it gets closer to the equilibrium ratio. So once again, comparing Q versus K, if Q is too large compared to K, that means the numerator is too high. That means your denominator is too low. As a result, to reestablish equilibrium, you're going to lower the value of P, you're going to increase the value of R, and as a result, get you closer to K. And so if you do that, you're basically shifting the equilibrium towards the reactants. So if Q is greater than K, the system, whatever mixture you have, it's going to shift towards the left overall. On the other hand, if you have Q greater than, nope, just kidding, if you have Q less than K, so once again, let's rewrite these just to make sure you have something to kind of discuss. Q is still going to be less than K, so that means it's going to be products over reactants, that time equals 0. What happens here? Well, that means my products are a little bit on the low side, right? The value is too low. The RO, this amount is too high compared to equilibrium amounts. So how do we make it go to equilibrium? Is that we use up my reactants and we shift it towards the right, towards your products, so that the values become a little bit closer to what K is, or it becomes closer to what K is. So to correct it, right, we shift towards the right. So in this case, we shift that way. Ultimately, it's really helpful to know, again, kind of the mechanics of shifting left, shifting right, based on the amounts that are present. But if you need to, just kind of remember that if Q is greater than K, Q is less than K, shift left, shift right. This kind of gives you a bit of a visual here. So this left side, or so in the middle here, we have Q equals K, meaning this test initial amounts, right? How does that compare to K? If it's equal, then we know we're at equilibrium. No need to do anything. However, right, on the left side right here, if Q is less than K, right, that means this K amount, notice how the value stays the same from here before. That means my Q is too little, so we're going to have to react and form some products. On the other hand, if it's too high, it's going to form reactants and shift towards the left. All right. So here's an example. Let's go ahead and work out these problems. This one gives you a synthesis of ammonia. The equilibrium constant is provided here. Predict the direction in which the system will shift to reach equilibrium in each of the following examples. All right. So you have three different problems. Let's do the first one together, part A. So as you might have acknowledged, there is no equilibrium equation given to you, but it is talking about the synthesis of ammonia. So we're making ammonia. And as you can imagine, this is going to be the same equation that we saw on the previous slides. Let's write it in. Boom, just like that. So for part A, let's go ahead and calculate Q. Q is going to equal to the initial amount of NH3 squared, that's given to us right here, 1.0 times 10 to the minus 3 molar squared, divided by N2 raised to the first power, so that's 1.0 times 10 to the minus 5 molar. And then you have H2, with this amount, 2.0 times 10 to the minus 3rd molar, raised to the 3rd power. All right. So again, we're calculating Q the same functionality-wise in terms of mechanics, the same way we calculate K. So let's go ahead and figure out what this equals. This ends up equaling 1.3 times 10 to the very large 7th power. Of course, there's no units with it. And so how does that compare? Well, Q is much greater than K in this case. So if Q is greater than K, that means there's lots and lots of my numerator present, right? Lots and lots of products. That means it's too much products. So to reestablish equilibrium, we're going to shift left. Shift left. Actually, I should write that out. Shift left to reestablish equilibrium. Go ahead and try B and C. It's effectively the same thing. Go ahead and calculate the Q, compare it to K, and then get practice determining which direction it shifts. One quick comment in terms of knowing the difference here is that you have to look at extent versus direction as two different concepts. The word of extent, by the way, a lot of times we'll talk about using the word lies. So that means we're going to have at equilibrium an amount of products and reactants that lies to the right, lies to the left, meaning that it's already established and one side is heavier, one side is favored over the other, one side has a lot more than the other. Whereas direction usually talks about shifting, or we talk about having Q versus K and using it to shift to then establish equilibrium. So it helps to know that this one, right, extent refers to already being established at equilibrium, whereas direction is about reaching equilibrium. What does it take to reach equilibrium? So let's go and take a look at this example. If you have some conversation where K is equal to 1 times 10 to the 5th, that's the equilibrium constant. So whatever reaction you have, whatever equilibrium reaction you're given, that value is just going to know, you're going to know that the equilibrium lies to the right, meaning that it's going to have lots of products versus reactants when it's at equilibrium. Shifting here, right, talking about the direction of the shift, it's not relevant here. It's completely irrelevant because we're not given initial amounts. We're not going to see how it compares to K. It's going to shift right, shift left. Is it too much products versus too little reactants kind of a thing? That's not discussed here. So we're simply saying if it's at equilibrium, if we know we have an equilibrium mixture, or we know we have some equilibrium constant present, based on that alone, we can make a decision saying that it favors the right, it lies to the right, it has a lot more products than it does reactants. On the other hand, like if we're talking about Q versus K, comparing these two ideas, right, Q is a reaction quotient, right, the test, comparing to the established K, then we know that if Q is less than K, we don't have enough reactants, right, the numerator is not high enough compared to the denominator to make it equal to K, so it's going to shift to the right. We're going to have it reach equilibrium by generating more products and using up my reactants, and eventually that's going to equal K, but at this point, it doesn't really matter. This conversation of where it lies isn't really important. Does it favor the right? Does it favor the left? It doesn't matter. Right? Does it lie to the left? Does it lie to the right? That's not what the conversation is about. It's simply saying to establish equilibrium, it's going to shift to the left. It's going to shift to the right. So this first one, right, talking about this guy, it's more static, whereas this bottom one, this is more dynamic. We're talking about movement. Finally, let's give one example anyway of how this works. If you look at the numerical aspect of this, it's going to calculate equilibrium amounts. So let's say that we have the substance dinitrogen tetroxide, but familiar, was used as a source of fuel on the lunar landers for the Apollo missions. Decomposition results in NO2. So N2O4 in equilibrium with 2NO2. If you don't remember, that's actually the same equation that we introduced this unit with. 0.133 is the equilibrium constant. Then it says in an equilibrium mixture, they figured out the concentration of N2O4, the reactant, is 0.500 molar. Determine the equilibrium concentration of NO2. The key word here is that they do tell you that it's the equilibrium mixture. So at this point, I don't have to worry about Q at all. I just have K because there's no initial amounts that I can then compare to shift. All I'm looking at here is simply using K. K is 0.133. Right, that's given to me in the problem. That's a 3. That's equal to my products over reactants. My product in this case, NO2. So NO2, concentration of NO2 squared, which I don't know any numbers, so I'm not going to plug anything because I'm not given any values yet. That's what I'm asked to solve for. Over the N2O4, which is your concentration of the reactant. You plug that in here, 0.005 molar. Okay, so let's basically solve. How do you get this amount of this NO2 concentration at equilibrium? Just basically plug it in as x. So I'll just rewrite it if you need to. 0.133 is equal to x squared over 0.500 molar. Solving for x. X is equal to the concentration of NO2. That's a 2. That's equal to 0.258 molar. And that's basically how you solve for it. Right? This is how you can apply the equilibrium amounts to solve using some equilibrium constants, any unknown concentrations. All right, that'll do it.